Okay, guys. So tonight I wanted to talk about creating cam from DXFs that were created in a different software. So the DXFs that I'm working from tonight were created by a River City Labs member in a software called DraftSite, and basically you wouldn't always do this, but it's really handy to be able to just pull some 3D CAD out of some 2D, or some 3D cam out of some 2D CAD quickly without having to recreate all of your geometry. So first thing we're going to do is we need to upload our DXFs into our Fusion360 project. So when you open up Fusion360, you'll see the project folders over here. I made a new project for cam class and a new project folder for the DXF class. And I'm going to click the upload button and select files, and I stuck them on my desktop for River City Labs cam class, and these are the two DXFs that we're going to work off of today. I haven't uploaded these yet, so I haven't actually ran through all of this, so you get to see all of the hang-ups. This isn't very scripted, that we may or may not run into. And if you guys have any questions at any time, go ahead and comment in the live chat box, and I will get back to you guys. So I'm going to start with the Bugang file. So what we're going to do is I'm going to just try opening it and see how that goes. A lot of times I will import it into another file that I have kind of set up, but I want to try importing and seeing how that works out. So it looks like everything showed up reasonably closed, which is what we want. I can tell where there are closed lines where the yellow is a little darker. So I'm going to close out this project. And when I set this one up, I set this up inside the material that I'm going to use. So I'm going to cut it from a piece of 24 by 48 inch HDPE. So first thing I want to do is make sure that everything came in the dimensions that I expected it to. That's 1219 millimeters. I'm going to go over into the model tree and change my units because I drew this in inches, or April did. Change that to inches, and now select the inspect line. Okay, so everything came in scaled appropriately. And if you're wondering what all of these dots are center points of the arcs inside the CAD geometry. So if you highlight them, it'll highlight the arc that it's showing. So we should be good to go for everything else that we need to do. So let's go into the model drop down and go select cam. And this brings us into the cam dialog box. Now the model tree changes. Our first folder is the cam root, and then it gives us the Bugang DXF that we can work from. So cam has a bit of a workflow. The first thing that we need to do is create a setup, and when we do the setup, basically what we're going to do is tell the CAD software where our geometry is in relationship to our machine. So the first thing we need to do is create a setup, and we're going to tell it what the work coordinate system orientation is. And the work coordinate system is the orientation of our coordinate triad here with the X, Y, and Z. And the last CAD class, Josh was asking why when you look at things, Z was pointing out, I think. And the answer to that is, in 2D CAD worlds, the way the coordinate system was always set up was X is to the right, Y is up, and Z points straight out of the screen. And that's how it's always been set up for the last 30 years. When we imported in our DXF, everything came in the right orientation, because that's how it was drawn in the 2D CAD software, which is nice. So I want my X along the long axis, because that's the long axis of my machine, my Y along the 24 inches, and then Z is up, because this is how it's oriented on my machine. And for the origin point, we're going to use this bottom left-hand corner. And I like working from the bottom left-hand corner most of the time because it feels like it makes sense. It's 0, 0 in the coordinate system that you would normally work in, but that can change depending on how you're holding your parts. A lot of times when I'm working on a mill and I'm holding a part in a vise, the vise jaw that holds this bottom left-hand corner moves. So I like to set it in the top left-hand corner because that's a rigid point that never changes. So it depends on how you're working, but for working in a CNC router, the bottom left-hand corner is almost always the right way to go. And the next thing that we need to do is tell it what kind of stock we're working from. And this is where one of the things that's really handy about using Fusion360 to do CAM off of a 2D drawing is I could have created a 3D model from all of this, but I didn't need to because we can use the stock dialog box to define our thickness of our material. So what I'm going to do is I'm going to say I'm going to make it from a fixed size box, and the width in the X is a 48-inch box. The depth and the Y is a 24-inch box. And then it's offset from the negative left side 0 inches. It defaults to center when you do this. And we're offset from the positive front side 0 inches. Oh, nope, that wasn't right. I closed out of it too soon. To get back into it, if you do what I did, you can right click on it and say edit. Or offset from the front side. And the height is 0.375 inches because I'm going to make it out of 3/8 inch material. And I'm offset from the top. And that's very important to note that the triad is on top of the stock and not on the bottom of the stock, because what that's telling the CAM software is I'm defining the 0 of my part as the top of my material. If I told it that I was defining it as the bottom of the material, that's fine, but we need to make sure that when we get to the physical machine that we touch off our Z0 from the bottom of the material or the machine bed instead of the top of the material. I like working from the top of the material because the top of the material is far more predictable on where it is than when you work from the bottom of the material and you just enter in a number for how thick it is. Because when you're working with stock materials like MDF or plywood, there's a very good chance that instead of being 3/4 of an inch, it's actually 19 millimeters. And 19 millimeters is 0.1 millimeters thinner, or 0.5 millimeters thinner than 3/4 of an inch. Or in some cases with plywood, it's can be up to an 1/8 inch thicker than 3/4 of an inch when you're working with 3/4 inch material. So it's nice to work from the top so there isn't any unexpected extra material, because you can always cut deeper, but if you ram your cutter through material you didn't expect to be there, it can be catastrophic in the most interesting ways. But one thing to note is when I created my stock, my triad for my 0 offset moved. So we want to go through and tell it that my stock box point that I want to work from is this one. This one. And that's interesting. It is slightly below my drawing. Well, let's see if that affects this. So click OK. And we will go through a couple different operations for this. This part here can be cut completely with the contour operation, which is this guy here, and all that does is the tool follows the outline. But I'd like to show a couple different operations and how they differ. So we will cover 2D contour, 2D pocket, and 2D adaptive clearing, because those are the most common. Didn't mean to click that. Those are the most common things that we'll use on the CNC router in the makerspace. And we can also look at the drilling operation as well. Before we do that, the next step that we want to do is we want to create the tools that we're going to use. So to do that, we'll go into the tool library, and the really neat thing about this is you only have to do this once. I personally have a whole bunch of cloud libraries that follow me around wherever I go, tied to my Fusion360 account. And these continually update as I add new tools to them, no matter what computer I'm on, which is really nice. As of yet, I have not found a way to do a shared library that's constantly updating. But what I can do is I can export libraries to help you guys get started with tool numbers that work well. Oh, Fusion hasn't updated yet. Okay. A new update hit today that changes the look of this a little bit. But basically all it does is it gets rid of this button, this button, this button, and a couple other buttons, and it puts them into right-click menus. Everything works the same though. So what we're going to do is I'm going to create a new library, and here, new tool library, and I'm going to call it RCL Cam. Well, once we're in here, we're going to create a new tool, and it's going to be a new mill tool. So everything that we do at the makerspace, you can use the tool number, length offset, and diameter offset of tool number 1. Because we don't have any sort of tool setter or anything like that, we don't need to worry about all of this. If you use other numbers, it can trip you up if somebody has been fiddling around in the tool table though. So try to stick to 1. Occasionally Fusion360 will get fancy and try to number cutters, and that can get annoying, but for everything that we're doing, tool number 1 is exactly what you want. So what we're going to do is we're going to create a new end mill, and it's a square end mill. And so what we'll have to do is we have to go through and find flat end mill, and we'll call it carbide. None of these actually matter, but they are kind of nice to have in your pocket later. What does matter is number of flutes. So for this particular part, I'm going to use a single flute end mill, and I'm not going to debate heavily types of tools. Just know that number of flutes matters. It matters that it matches the cutter that you're using. And it is a 1/4 inch, so it's 0.25 inches. And the flute length on it is 0.75. And basically what that says is 3/4 of an inch, that end mill is effective for cutting. And it is a 1/4 inch in diameter. And the rest of these matter for simulation purposes. They don't really affect us for how we're utilizing these tools. And the next tab that does matter is the feed and speed tab. Now, I've gone through and I've created a spreadsheet of different feeds and speeds that I know work well with different materials, and I'll link that in the video description. And I'll post it in our Slack channel as well. But for right now, looks like we're coming back. Okay, stream resumed. Okay. Feeds and speeds. The first thing that I'm going to do is I'm going to put in a spindle speed. Now, because I'm using a single flute cutter, I can go significantly higher. We're cutting this in 3/8 inch HDPE. So instead of 15,000 RPMs, let's do 22,000 RPMs. Now, notice that when I change this number, the surface speed number and feed per tooth number change pretty significantly. Surface speed is how fast the actual outer surface of the cutter is moving. And feed per tooth is how much material will be removed from the part at every revolution of the cutter. Surface speed matters much more with lathes, but it's how a lot of machinists will communicate how fast you want to cut, particularly with drills. And feed per tooth is probably the most critical real number. Now, most of us work in feed rates of inches or millimeters per minute. I like to think in inches per minute, even though I typically design in millimeters, and I know that drives a couple people I work with nuts, but it's how I've always worked. So for the HDPE, I'm going to cut at 50 inches per minute. And that's a pretty safe feed rate for the cutter that I'm using, and I know it'll give a good finish. How I know that is based on experience, but also feed per tooth. 22,000 RPMs at 50 inches a minute equates to about 2¼ thousandths per revolution. That is enough of a feed rate to create a really good chip, so that we're not creating heat, we're not creating friction, we are cutting and removing material with every revolution. This is critically important to things like not melting aluminum into your cutter, or not melting plexiglass or acrylic into your cutter, as well as not just breaking your cutter off into the material. Fred says I went offline. I should be back. Now, there are 4 different feed rates here, and they all matter. The cutting feed rate is the most critical feed rate. This is the feed rate that our cutter will be going through the material as we're cutting. Lead in and lead out are also important because those are the feed rates that the cutter will enter and exit the cut at. Usually you want to run those a little slower. So we'll say 40 inches a minute. And a ramp feed rate is any time that we are moving down in the Z direction as well as X and Y. It always slows that number down quite a bit because depending on your cutter type, it may or may not be able to cut in the Z direction. A number of cutters aren't center cutting is the term. For plastics and woods that we run on the CNC router at the space, it almost never matters, but it is important to pay attention to once you get into metals. For this, I'm going to change my ramp feed rate to the same as my cut feed rate because I'm cutting soft plastic, and I know that I can. And the last feed rate is vertical feed rate. So this is if we are plunging directly into the material, like if we are drilling a hole with our end mill. That is going to be significantly slower because of how we're removing the material isn't the way the cutter is optimized to remove the material. But I also don't like the fact that we are removing less than 1/1000th per revolution. Even though we are cutting an HDP. So I'm going to change this number to 0.001, which ups that feed rate to 22 inches a minute. It's soft plastic, it should be okay. And the last thing is post-processor tab, which we don't use. So that's our 1/4 inch flat end mill. I'm going to create one more tool, and that is a drill bit. Almost all drills have 2 flutes. I don't know why it defaults to 3. It seems to always default to 3. Our unit of measurements in inches, I'm going to call it a 0.5 inch drill. Not 0.5, but 0.5. And all of these numbers are fine for what I'm doing. And then our feeds and speeds. Spindle speed. The router, the bottom end of the spindle speed of the CNC router at the makerspace is about 8,000 RPMs. I wouldn't run it under 10,000 RPMs because it's an air-cooled spindle. So it needs the RPMs to keep the spindle cool. Spindle that I have on my router at home is a water-cooled spindle, so I can run it all day at 8,000 RPMs and it'll be fine as long as my water pump's still going. The one thing to note, though, is the relationship between surface speed and spindle speed. For an example, when you're using a 1/8 inch to 1/4 inch drill, the recommended surface speed in aluminum is 300 to 600 surface feet per minute, if I remember that right. So if I change this to 300, it changes my spindle speed way down. But if I change my feed rate to 10, oops, it doesn't affect my surface speed. But it does, but surface speed does affect our feed per revolution because it's related to this. So sometimes it's kind of a game to get your numbers in the right range, but also the right surface speed. We can talk about that all day long and debate it on what's right and what's wrong. But put that. All right. So that's the tool dialog box. So tool dialog and setup are the two things that usually catch people when they're first getting things going, because they're not super intuitive that you have to do them, but it's important to do them in the right times, because you can edit tools in process, but it doesn't work as well. It doesn't give you as many options. So the first thing I want to do is I'm going to drill a couple holes in this. So click the drilling process and the drill tool, and we'll go to the RCL cam library that we created, and it defaults to only showing drills, which is nice. You don't have to sift through a whole bunch of drills that we don't want to look at. Click OK. And then it imports the feeds and speeds that we set back in the tool library. Now we can change these here all we want, but what that won't happen is any changes we make here will not update in the tool library. If we go into the tool selection dialog box and select this and select the edit tool button, we can make a change. And it'll give us this dialog box that says the following operations are using this tools, but with a different feed and speed. So what it's saying is, hey, you already had this selected with different feeds and speeds. Do you want to override that, or do you want to keep everything the same for those operations? I want to override it. And now our spindle speed and surface speed change to what I input. I want to select the hole faces that I'm going to use in this one. So what we can do here, since there are no hole faces, we just have circles, is we can actually select the points, the center points. Hey, or we can't. Selected points, there we go. So we can select the center points of these holes, or the radiuses that we created here. And then the next tab over is the heights. So this is critical, especially when using a router with drill bits, because drill bits tend to be very long. And it's important to always make sure that you have enough Z clearance to complete the move. Because we have a machine that uses stepper motors, it doesn't care whether it completed the move or not. All it does is say, hey, I told you to move 9,000 steps, and I'm done telling you that. I'm going to move on to my next command. It doesn't check whether it actually moved that distance. So what would happen is it would jog up in Z, it would stall out, and then it would jog over to the next hole and then ram the drill bit straight through the table. Don't ask me how I know that. I'm promising you that it is the truth. So what we need to do is we need to say that the retract height, and that is how far up the drill pulls from the top of the table. This is the retract height, is a reasonable distance. 0.4 inches is fine. The stock, or that's the clearance height. The retract height is how far it pulls up between holes. So that is this height here, this yellow one. The feed height is where it will start feeding from. So it is 0.2 inches from the top. So it will be a rapid move, which is the fastest that the machine can move, until it gets a little under a quarter inch from the top, and then it'll go into the commanded feed speed, which is 20 inches per minute instead of the 100 inches per minute that it would move before that, traveling. And the top height is the top of the material. So normally hole top is the default selection. I'm going to pick stock top for this because I know that for some reason the stock was defined slightly under the DXF. And for the bottom height, I'm going to say stock bottom. And it's important to note here that it only takes the drill to the tip is at the bottom of the material. So it doesn't drill a hole all the way through. This is how any drilling operation is handled. Basically what this does is it drills only deep enough to not drill into your machine table, and then you have to explicitly tell it that, yes, I do want you to go all the way through the material, that's okay. And we do that by clicking drill tip through bottom, and then I will normally give it an extra, I don't know, 30 thousandths of through, just to make sure it makes it all the way through the material and that we have a nice clean hole. Since we're running on a router and we've got an MDF spoil board, that's okay. And then the last thing is the drilling cycle type. There's a number of different options in this. The options that we will normally use on any of the machines in the makerspace are drilling rapid out, which means it'll just drill all the way through at the commanded feed rate, which in this case was 20 inches per minute, and then it will pull out as fast as it can once the hole's completed. We'll use chip braking, which means it will feed in at the commanded feed rate and pull out after a commanded distance, say 0.03 inches or 1/8 of an inch. It'll drill down and then it'll pull out a little bit just to break the chip. This is really good for stringy materials like HDPE, and this is the operation that I'll use for this. Or we can use deep drilling, which will drill down a little bit and then it'll pull completely out of the hole to clear all the chips out of the drill bit. I'm going to use chip braking and set the peck depth to 1/8 of an inch. That's perfectly fine for the plastic that we're running. And then these defaults are all okay. The nice thing is, as you go through this, if you just hover over the cursor, it will kind of give you a description of what each box will do. Click OK. And then it gives me a little preview of the operation that it created. And we can go into Simulate, right click on it, and check the stock box, and it will create a simulated stock representation and go through and drill each hole. What it doesn't do is it doesn't simulate the pecs, and that's fine. So we'll turn the drawing back on. And the next operation that we're going to do is 2D pocketing. So we'll click on 2D pocket, and I'm going to select the 1/4 inch end mill that I created in our RCL cam library. And select geometry. So for this one, I'm going to select this geometry here. And you notice when I clicked it, it selected the entire outside material. That's not what we wanted. What I wanted was to just cut out this inside. So this arrow here defines which side of the line the end mill is going to cut on. Now for the rest of this, we don't need to check anything. The only one that is useful occasionally is rest machining, and what that does is if you had a larger end mill, say that you wanted to clear out a bunch of this material with, and then you wanted to go back with a smaller end mill to make the corners nicer or something like that, you can check rest machining and it'll look at the previous operations and say, hey, you already removed all of that material, we don't need to do that again. And then I'm going to check my heights again. So the retract height is reasonable, but we need to define the top. So we're going to run from the stock top, And the bottom height is going to be the stock bottom again. And passes. There are multiple boxes in this dialog that are important. Maximum step over is a big one in this. Basically what this says is every time I make a new line, I'm going to cut this much material out. Now we have a 1/4 inch end mill, and it is taking, what is that number? A whole lot of material. A large percentage of the cutter. I don't like that. I don't like taking more than 40% of the cutter width. And in this case, let's take, we'll just do point. And we'll do multiple depths. And what this does is, without checking this box, it would plunge down all the way through the material and take all of that out at one time. With multiple depths, we can only take out. Alright, stream's back. Sorry about that. With multiple depths, we can take out only 1/8 of an inch at a time, or 1/16 of an inch at a time, or even more. Since we are doing 2D pocketing, I want to make sure that I'm not taking too aggressive of a cut. So we will take half the cutter width, which is 0.125 down. And that's about the max that I would want to do using the 2D pocketing. And when we step over to adaptive clearing, we can take more than that. The last thing is, I guess not the last thing, stock to leave is checked by default. This is important to leave checked when you're doing anything like pocketing or adaptive clearing, because it will leave little scallops on the sidewalls of your material. So it's nice to be able to go back and take a nice finish cut for that. And the last thing is, I like turning on smoothing, especially for Linux CNC based controllers. What this does is it takes nodes out of the line. Basically, it makes the line finer, and it reduces the size of the code and the accelerations and decelerations on the machine. Because every line of code that's created, every node that's created in the line, it creates a ramp up and a ramp down, even if it's a continuous move. So things start to travel much faster and much smoother when you turn on things like smoothing. And the other one is feed optimization. And when you're doing internal pockets like this, feed optimization is a really nice feature to have. End mills really don't like internal corners because the way the cutter is engaged, it goes from, in this case, having 0.1 inches of the cutter engaged, so a little under 40%, to suddenly 90% of the cutter is engaged when it hits a corner. That rapid change in cutter engagement in plastic isn't such a big deal, but when you get into cutting steel or even aluminum, it can create chatter and harmonics, which create broken cutters, which just creates frustration. So I always check feed optimization and smoothing. And the last couple things are lead in, lead outs. For this, I'm going to turn them off because it's an internal pocket and I want to make sure that this outside stays nice. And the ramp type is a Helix, and I'm going to, I normally would leave 2 degrees, that's a fine number, but I want to make that a little more aggressive. So I'm going to make it 4 degrees because we're cutting soft plastic. We'll click OK. And that created our pocket. So it created this nice 4-degree helix where it enters into the cut. And it creates a nice even line that to our eye is nice and pleasing, and it looks like it makes sense, right? So let's simulate it real quick. Stock's turned on. So we're going to helix down in. And notice how I go from there, suddenly the full width of the cutter is engaged in the part. That's where feed optimization turning on comes in handy. Because even in a soft plastic like HDPE, I've seen cutters break with that sudden engagement. Okay, we don't need to watch all of that. Now the next one is we're going to do 2D adaptive. And 2D adaptive effectively does the same job as 2D pocket, but it doesn't look as nice when you just look at it. But what it does do is it keeps a constant cutter engagement, which means we can cut much harder and much faster without sacrificing end mills or cut quality. And it's pretty awesome. So I'm going to select that guy again. And this time you notice we don't have the rest machining option. For the bottom height, I'm going to select stock bottom again. And top height is stock top. And notice this time my default optimal load was 0.1 inches instead of 0.2375 something. And that's just because the way adaptive is done, it's more optimized for cutting quickly with less cutter engagement so that it all just kind of works nice. Now, what I am going to do this time is I'm not going to check multiple depths, because that lower cutter engagement and the way that it generates the toolpath, it'll remove all that material and it'll be fine. I am still going to leave stock to leave on though. Turn on smoothing, turn on feed optimization, and this tab I almost always just leave alone. Everything is typically just right. But I am going to change that ramp angle to 4 degrees again. So we'll let it generate the toolpath. So when you look at these next to each other, notice how different it is. So in this one, it's a constant feed move with consistently changing cutter engagement. With this one, we helix in, and then we start helixing out, and then we're constantly keeping the cutter engaged unless we're traveling. And it's got lots of rapid feed moves where it's traveling. Oh, I guess it's going down, coming back, going down, and keeping these nice arcing moves in. The end mills really like that. So let me highlight both of these, and we'll simulate them together so we can see the differences. And we'll hop over to the next op. So we're helixing and then helixing out, keeping things nice and consistent for the cutter engagement. Now, I've worked with a lot of people who really don't like this method of machining, cutting tricoidally because they don't like the way the cutter moves. They find all kinds of excuses for it, but it has always been consistently better for me. And the tool marks just look awesome. One of the arguments that they give me is time, so I want to check something real quick. Do multiple depths, and give it the same step down, and we can check how long these operations take comparatively. So machining time for this one is, total feed time is 4 inches. Total machine time is 4 minutes and 58 seconds. I bet you this is very close. Oh, almost double. Okay. 10 minutes. We can run this faster, though. Anyway. Moving on. So the next thing that we need to do for both of these operations to clean up their outer walls is to run a contour pass. So contour just runs the cutter along a path. And it gives us a couple other options now. So we can do rest machining with contouring, which is where we would use a smaller cutter to clean up corners, or a finishing cutter to give us a nicer finish or something like that. And the other thing is it gives us tabs, and we'll use tabs on the next operation. But what tabs do is it allows us to leave a little bit of material in place so that we can keep our parts down. So for our contours, just like these, and the bottom, again, we'll select stock bottom. And because we have already cleared out all of the material, we don't need to do multiple depths or stock to leave or roughing passes or anything. I'm just going to turn on smoothing and feed optimization. And this time I'm going to leave lead-ins and lead-outs on, and I'm not going to turn on any ramping because there's no material there. So we can just plunge down in, and it will do a quick lead-in, follow the contour of the part, come out, lead out, and then go up. Simulate that. Actually, let's do this. So you can see the actual state of the material. I'm going to simulate all three, and I'm just going to... Went too far. So this is the state of the material when these operations start. Click play. So it's just going to go around, do a skim pass on the walls, and now the contour. Okay, so we've done drilling, 2D pocketing, 2D adaptive clearing, and those are the consistently used ones. The last thing we'll do is we will do a contour pass to cut out the full geometry. So almost all the time it will leave the last tool that was selected in the tool selection box. The only time it doesn't do that is when the tool doesn't fit the operation. Like if I was trying to do a contour pass and I had a drill bit last, it would give me a red flag that, hey, you can't do that. So our contour selection, this is where the DXF might get a little hairy because these are line segments and not a polyline. So let's see. We'll have to select all of these. That's going to get hairy. So when this DXF was created, normally I would, before I output the DXF, I run a command called pedit, and I join all of these line segments together. And I didn't do that on this one because I was in a hurry, and I kind of wanted to see how well this would work. And now I'm regretting that. But now you guys know. So we need to make sure that the arrows are all pointing in the same direction and on the same side of the line. These little tiny guys. Kind of hard to see. We'll see if it gives us an error. Alright, so arrows are all flowing seemingly the right way, which means the cutter should be consistently on the same side of the line. So the next thing I need to do is tabs. And tabs are important, especially for material like this, where the material is kind of thin and might spring open as I'm cutting it. One of the things that I've noticed with HDP is sometimes it has internal stresses that as you cut it, it relieves them. So like as we cut these fingers loose, this part might kind of pop up. And that's fine if we don't travel in that direction ever again. But sometimes when your parts pop up, like you might be cutting a pocket over here and then suddenly rapids over here and then rapids through your part because it was taller than it should have been. So we're going to use tabs. Now this is way too many tabs. And that's because the tab's positioning is set by distance at every 2 inches. Let's do it every 6 inches, looks like. That's way more reasonable. Now remember, when you're placing tabs, that any tab you put in, you have to cut out. So if it's in a precarious place, like in the root of this guy, that will not be fun to cut out. So it's good to go through and check these. It's also important to remember that you want tabs where you want them. So, oops. I didn't see any tabs on the outsides of those fingers. So maybe I need to change that number a little bit more. There we go. So now there's one there. Okay, that should be good. Tabs are always a game. The other way that we can do this is we can say at points. And at points is really useful when you have a small part. When you have a very long part like this, it's really frustrating because you have to go through and place them all manually. I don't want to do that. The other thing to note in this is there's 2 types of tab shapes. There are rectangular tabs, which are great for strength, and in material that it doesn't matter that you're plunging, they're fine. So soft plastic and wood, no problem. With any metals or hard plastic, though, triangular tabs are your friend. Because what they do is they create this nice ramp back into the material, and you're not plunging your end mill into your material. So for this, I'm going to leave my tabs rectangular because that's how I want them for this particular material. The tab width, 1/4 inch, is fine. And the tab height, 1/16 of an inch, I'm going to make them thicker. I'm going to make them 1/8 of an inch. Because HDP tends to be a little wavy sometimes, and I don't want to have a part where the material had bowed up a slight bit, and all of a sudden my tab is non-existent because I made it too thin. That's almost worse than not having tabs. Almost. Again, in this, I want to do stock bottom as my bottom height, stock top as my top height, and I'm going to do multiple depths this time. And my multiple depths, I'm going to set at 1/8 of an inch, so there's going to be approximately 3 passes, because it's 3/8 of an inch. And I want to set smoothing and feed optimization. And I want to do lead ins and lead outs because I don't want when you don't set lead ins and lead outs, you tend to have 2 lines separated by about 1/4 inch on the edge of your part where the end mill plunged in and lifted out. So I don't want those on there for this, so I'm going to set lead ins. And I'm going to do a small ramp in because I don't really want to plunge either. Okay. So you see here it does the lead in and then it ramps down to cut depth and follows the contour. If we look at it from the top, the blue line is on the outside of the purple line, which is exactly what I wanted. But it gave me a warning. What was the warning? Open passes are linked with both ways zigzag ramp. Huh, that's interesting. Let's simulate it, see what it did. I have a feeling because those were open line segments, it didn't quite know what to do with it in some spots. Yeah. It looks like it's still going to cut okay, but I think I'm going to take the helix back out of it. Or the ramp. Let's see if that makes it a consistent path all the way around. Looks like it still has a lead in and a lead out right there, but it's less detrimental than the multiple ramps. Okay. I like that. I think that'll work well. And we can speed this up, make it go real fast. Do a front view. And we can see our tabs in there. So everything looks okay. Alright. So now that we have our tool paths that we want to cut these out, we drilled some holes, we pocketed some of these guys out, contoured them to give them a nice internal finish, and contoured the outer sides of the boogang. Now we need to turn this into code that the CNC mill can deal with. And to do that, we need to run a post-processing script. So to do the post-processing, we can right-click on the setup if we want to output every operation as a single program, or we can output each one individually, or you can control-click on them and output them. Say we want to do the pockets as a single program. I can control click on them and select them, and then say post process. And when we post process, basically what's happening is the cam CAM software is creating this in a language called apt. And apt is a machine language that is like a step above assembly, and it is very consistent across almost all CAM softwares. What isn't consistent is how machine tools take that code in and read them and then turn them into machine movement. So we need to run this through a code generator called a postprocessor that takes in that apt data and outputs it into machine readable G code. And the post configuration that we need to use for the machines at the makerspace is the linuxcnc.cps generic Linux CNC EMC2 post configuration. Now this always has an extension of ngc, and it has a couple options in here, and all of these, the way they are set are correct. You don't have to fiddle with this at all. The only thing you have to do is drop down the post configuration box, find linuxcnc.cps, and give your program a name. So we'll call it Boo Gang. I don't remember how to spell it. There it is. Pockets. And if I'm outputting multiple programs at a time, I like to give them descriptive titles like Boo Gang Pockets -25 to denote a 25 millimeter end mill, or a 0.25 inch end mill, sorry. And then in the program comments, I will usually write in what tool I'm using, and if I did something silly like put my machine 0 in the center of the part instead of the bottom left hand corner, I'll write that down too. So we'll say quarter inch end mill, G54, which is the coordinate system that we used, bottom left corner, stock top. So that just helps me remember, if I go to run this program 2 days later, where did I stick all this stuff and what tool did I use? It's helpful. And the only other thing in here is we can select an output folder. So this always defaults to this app data folder, which is impossible to find because it's hidden. So you want to make sure that you click on this and you stick it somewhere that you can remember. So in this case, I'll make it the CAM class folder and post it out. Save it, and then it will open it up in the text viewer of your choice. I like Sublime Text, and you can go down through and read through this code. If you know what you're looking at, it's nice to go through and look at it and make sure it looks sane. If you don't know what you're looking at and you have questions, you can come get one of us that do have a pretty good idea of what we're looking at, and we'll go through some basic G-code stuff in a later class. There's just too much to cover right now, and we're already over time. Important things to note, though, are that it came out with your comments that you want. The tool number looks right, so tool 1. And all this stuff looks reasonable. So from there, we can copy this onto a flash drive and take it to the machine and start running it. So if you guys have any questions, hit me up on the Slack channel or any other way that you have to get a hold of me. You can leave comments in this video, I think. And I hope you guys gained something